So, Alex gave a nice overview of how to solve a problem on D-Wave's QPU, and nice overview of our Ocean stack, Ocean SDK. So how to map specific application domain problem onto something that we currently support, like graph mapping or constraint compilation, and then to map that onto a BQM. And then when you have BQM, you can use some of the samplers to solve them. However, the problem Alex mentioned was with what if your problem is too big to fit the QPU, then you need to resort to decomposition. You need to slice the problem onto smaller problems and solve each small problem on a QPU. And D-Wave Hybrid is a framework we developed it fits in this layer of samplers. It allows you to construct a new sampler, which is a decomposing sampler. So hybrid stands for actually Hybrid Asynchronous Decomposition Sampler Framework. It's a minimal Python framework, heavily leverages Ocean tools, and it's built on top of Ocean tools. And the actual framework is just a minimal syntactic glue that binds all that together, and it allows you to leverage quantum and classical resources, because as Alex mentioned, you sometimes want to solve some of the portions of your problem on a classical or some subproblems classically and some quantum using a QPU or some other quantum machine. So you need to have a way to combine those easily. And since they're hybrid, basically, as you will see soon, is a data flow programming model paradigm kind of language. Independent parts are executed concurrently, and the concept of decomposition is inherent. So usually, when you want to use hybrid, you have a large problem. So problems are broken into pieces. And the concept of probabilistic sampling or probabilistic approach is embedded or core to hybrid, because we use sample sets or sets of samples to represent our solution. So, quick motivation. Imagine you have a pseudocode for your algorithm you want to use. It starts like that. So you see you have some taboo search over there. You have decomposition based on energy impact of variables at a particular sampler that you're deconstructing your problem at. Then you have some loops. Then you have some sampling on a QPU, and that usually translates to 1,000+ lines of C code. Specifically, this is QBSolve, and this is QBSolve's code in C. And now imagine you can represent more or less the same algorithm using a few lines of Python code and a few blocks which are understood, which you can tweak, or you can even create your own blocks. But the point is, the structure is visible. So the functional structure is like this of the solver. You can see immediately you have a loop which in two branches try to run taboo. In parallel, it decomposes the problem based on energy impact, sends that off to a QPU, the one problem, combines the sub-solution back to a global sample, picks the better one. So, by the way, this red arrow here means in the racing branches, which I'll mention briefly later. The concept is once the one branch is done, it'll interrupt the other one. It'll get the best solution from that other branch. It'll incorporate that into the final solution. So we pick the better solution here by this argmin block, and we'll loop until some condition is met. So the idea is to visually outline the algorithm for code to be easy to tweak, because you can easily tweak parameters, you can easily tweak structure, and also to extend, you can create your own blocks. And benchmarking profiling is one of the core features. So we profile by default, and but also on the other hand, we wanted to balance simplicity with expressiveness. So this is not as general as it could be. It's not a you cannot build a general graph. You cannot build a TensorFlow kind of model with this because we wanted to stick to functionality usually required by algorithms we studied for decomposition. So, and we wanted to provide a library of such building blocks, which are then understood and easily extendable by developers. So, quick demo. I'm not sure you can see the code here. I can actually run the demo on the system, just for why not? Because this is a short presentation, so I might as well spend some time on a live demo. And by the way, we have a higher latency here from Europe, but I can still ping the system. And this Wi-Fi is not that fast either. But okay, so the total runtime for one sample is or one sampling is 1.5 seconds, which is pretty slow. But have in mind that it's Wi-Fi. It's Europe to US connection. But never. So can you see? Yeah. Just a short piece of code. So this is the workflow which you saw previously, and then just before running that, okay, actually not. It's not. I'm lying. This is another one with a simulated annealing subsampler here, and not QPU one. So I actually need to use the QPU. Okay, I'll use this one. Sorry. So now this is a little bit slower because the QPU block actually in this step where we are actually constructing the runnable object, we are contacting D-Wave and fetching a list of available solvers and picking the first one which we'll actually use for QPU sampling. So the workflow is defined. BQM for this demo, I'll just use the simplest possible BQM you can imagine. Just a triangle with ABC nodes, and it's a kind of frustrated triangle. And then based on the BQM, we will construct a state, a hybrid state, which looks, it's more or less glorified dictionary. It contains the problem and samples, but you can put whatever you want in that state. And then you run the workflow like this, with some state. Oops. You get the feature back. And it's still running, so it's sampling. It has several iterations it needs to do. It's done now. We can see the results, and the result is a final state, which in this case you can see the energy is -3, and that's the ground state actually. So yeah, back to this. It's more or less that. As you might have noticed, the basic block is the class is a runnable type actually, which is composable top-down, as you can see from the example there. And this is the one representation. This is maybe a more readable representation of the flow which is being executed here. So we have branch, tracing branches, arguments, samplers, and all that. All components are runnable types. Runnable takes in a state and produces another state. It's executed synchronously. You can control which executor is it run in. And also, every runnable implements some traits, and traits constrain connectivity with other blocks, and also constrain input and output states. And every runnable is profiled by default. So The other primitive of importance is the state, which is something like a immutable mapping type wrapped in a feature. It's passed between runnables. It carries whatever you need to do. You need to carry between runnables to solve your problem. Usually, that's at minimum that's a problem and samplers, or subproblem and subsamples. And compliance is for the input and output states is checked on runtime by each runnable. So I would like to walk you through a small build-up of that simple example that we just saw. So one way to modify the workflow is by tweaking parameters. For example, in the first example, we on each iteration we took only first subproblem. Over here we're saying let's do rolling decomposition of 15% of the problem, and on each run take some other subproblem until you reach the 15% of the global problem. And you can control, for example, the convergence criteria for your looping and things like that. But then you can easily also modify the structure. You can say, okay, let's not just run one subproblem on each iteration. Let's unwind as n subproblems, depending on the size of the problem. And by the way, the size 50 there, that's the size of the generated subproblem, which will be then mapped onto and solved on the QPU. So, for example, if you're solving this on a 1,000 variables problem, on each iteration you would have like 7 subproblems or something like that, and then you would run those 7 subproblems in parallel on a QPU, because you see we have a map reduced here. So we would run the same set of subproblems to 7 basically parallel executing QPU subsample blocks. We would reduce the results into one, and we would use that to inform and to generate a new or a next state, the next sample, which might be better or not than the one we got by the taboo solver. Another extension, let's say instead of just running QPU in parallel on all the subproblems at once, let's run maybe some other class, maybe some other sample, maybe simulated annealing, maybe just try with random variables, random values, so we might escape the local minimum like that. And then you see the subsampler is defined as a parallel execution of QPU, and in this case random subsampler in the workflow. And as I mentioned, and by the way, on the right hand side you can see this current structure of the QPU that Alex was refraining from talking, because I think it's important to understand that we are dealing with a finite limits. And this is a particularly bad yield. This is not what we have in production, but so in production we have more or less full yield, and that means that every qubit is connected to exactly 6 other qubits as it should be connected. You see some connections here are missing. So this is just one of the limitations you need to deal with. But decomposition is more general than that. I mean, when you're trying to multiply two big integers, if you cannot do it in a single cycle, you need to divide the problem and divide and conquer, right? So QPU and annealing could be thought of as we call it, the quantum machine instruction. So one anneal cycle is actually execution of one instruction, and instruction acts on a problem, which is a full BQM, and gives you a set of samples. The thing is, decomposition is, there's no such thing as a general decomposition. You can't have one algorithm which will apply to any problem you have. You will need to tailor the decomposition algorithm to the problem you have at hand, and obviously to device, compute device. There's a paper called No Free Lunch which talks about this. On the other hand, there's no shortage of ideas for decomposition, how to do it. So there are many heuristic approaches you can try. And also hybrid solvers, there are really many ideas how to implement them, how to approach them. And why I'm talking about this? Because it's easy to construct your own runnable. You just need to extend a few methods there, and you can easily implement a new control flow block that you're missing in hybrid. You can implement a new decomposition strategy you might have, or a new sampler, for that matter. And we actually would like you to do that. It's open, it's free, so that would be great. And by the way, here on this picture here, we see the profiling thing by default. So the timers and the counters that we have, this shows for example, in this sleeper runnable, we are sleeping for 3 seconds, and we can see that dispatch next, the total execution is 3 seconds, because that's how much it took for racing branch of taboo and sleeper to finish. As I mentioned, contributions are very welcome. We have a list of ideas for things that could be done. I mean, it's idea of hybrid is in early developer preview state, so things will be changing a lot, and not all of these are created as issues on GitHub repo, but they will, especially if someone is interested. Tomorrow we have the workshop, so if someone wants to hack a little bit, that would be great. Oh yeah, and you told me I need to include the developer survey. We have a survey out, in which we are trying to get a better feeling of developer requirements for hybrid and for Ocean tools. So if you feel like would like to contribute, that would be also great. And the slides are available online, so you can see the link there. Yeah, that's it.
Any questions?
Go ahead.
What is the largest number of variables you could imagine to solve using this hybrid approach? Let's say in a reasonable time, let's say half an hour,
Yeah.
for example.
Okay. So the question is, what's the reasonable number of highest number of variables a problem could have we could tackle with this approach? So actually, I'm experimenting with problems of size 2,000, 2,500 variables, and I think we can with some optimizations we can go up to maybe 10,000 variable problems. But yeah, so for now I would say around the realm of thousands of variables.
But 2,000 is what you have on D-Wave already.
It's a good point. However, that's with the limited connectivity, right?
Yeah.
So imagine you have a fully connected 2,000 variables.
Okay.
Then you need to somehow decompose it, run it in sections and things like that. So that's, yeah.
Thank you.
Yeah. Go ahead.
You mentioned at one point that you could use different methods to escape local minimas.
Mm-hmm.
So I was just wondering if by default the whole strategy is it theoretically not guaranteed? to give an answer which can escape local minima. So the local minima problem still exists, even though maybe the system is simulated on a completely quantum hardware. So the local minima problem, does it still exist there, or somehow it's circumvented?
So the question is about escaping local minima, and isn't that solved by a quantum device already? Something along those lines. So the thing is, sure, if you can solve, if you can fit your problem on a QPU, and you can solve it on a QPU, most likely it won't. You won't get a local minimum. You'll get some of the better solutions, although it's a probabilistic, so you might get some of the not so good solutions. However, when you're decomposing a huge problem, and I mean, as Alex mentioned, we're working on problems of size hundreds of thousands of variables, and eventually, hopefully, hybrid will get there. It's not quite there yet, but the problem is when you're decomposing and solving small problems, then you need to have some heuristic algorithm, optimization algorithm to escape local minimum, right? Because only a sub-problem is free of that, which is solved on a QPU. And you still have a larger problem, and when you combine sub-problems and solutions to sub-problems, then you might still get non-optimal solution, right?
So sufficiently large system could escape this problem altogether?
Yeah, exactly, yeah. Ideally, you would have a sufficiently large system, yeah. Anything else? Okay.
All right, if there are no more questions, then let's thank the speaker one more time.
Yeah.
We had two talks about D-Wave